as you have seen PyLabRobot be developed and maybe contributed to it handling other types of devices outside of liquid handlers, I don't know, is there anything that's been surprising or fun or particularly challenging in working with, a flow cytometer versus a heater shaker versus, other types of devices?
Yeah, so every device it kind of speaks its own language. So when you think about these machines, in the end, there's a USB cable that comes from the machine that goes into your computer, and there are some data, some bytes that are flowing over this cable. And those bytes, they're sort of structured in a specific language. Just like you and I, we communicate in English right now. We could maybe communicate in some other language. It's the same for devices. They communicate in a specific language over the USB cable. And so there's a lot of differences, even between machines of the same kind, how they represent their data and how it is sent over the cable. For some of them, it's easier. For some of them, it's more difficult to figure out what's going on.
Is the easiness or difficulty generally correlated with the brand of the company or the type of device? What have you seen?
I would say it is correlated with the type of with the company, just because they employ specific people who like to do things in specific ways. Not necessarily to think about people writing their own interfaces. More so that it's just how they like to work, which languages they write their software in, for example. And then I would say it's really correlated with the type of machine. You can imagine for a skill, there is a single command, get the weight, and then there's a single number, which is the weight. And maybe there's like a zero function or a tare function. But they're simple machines, so it's simple to figure out what the language is. And then for liquid handling robot, which is this very big general machine, it's going to be a little bit more difficult. But that's only weakly correlated. For some machines, the language is incredibly complicated. For example, for a centrifuge, the language was one of the most difficult ones that we have seen, even though it only spins at a specific speed and opens and closes the door. Yeah.
Wow. So could you maybe give us, put us in your shoes. You've got a new device, or just the community is trying to integrate a new device into PyLabRobot. You mentioned there's data flowing over a USB cable. What does I don't know if reverse engineering is the right term, but what does the process look like of integrating one of these devices into the PyLabRobot sort of ecosystem?
So just like how there's a bunch of variants in devices, I would say there's a bunch of variants in how you integrate a device. If that weren't the case, I would have written an algorithm to sort of automatically implement all of them. And unfortunately, that's not possible. So for integrating a device, there's sort of different ways that you go about it. In some cases, there's documentation available on what the language looks like. So this is like the firmware command set, for example, and how does a machine talk over the USB cable, which is sort of like the easiest example, which on the one hand I enjoy because it's fast for me to add a new device. On the other hand, I do like to solve puzzles. So for other devices, there is essentially no documentation whatsoever. Maybe within the companies, like one or two people know about the protocol. And so really there you just use this program to observe or kind of sniff the bytes that are flowing over the cable. And then you get a bunch of bytes on your computer. And then my job is to analyze, just stare at the bytes. How is the data that I sent represented? And there are some general strategies here. So for example, I always like to send a single command to the machine that's very simple. For example, open the door. And then I look at the commands that I have captured. And then I send another command, for example, close the door. And then I see maybe 1 or 2 bytes different between those two captures that I made. And so I know probably one of these bytes is going to be the command for open the door. One of them is going to be for close the door. And so you have an hypothesis. And imitating the scientists at my company, I then have a hypothesis, I'm going to test it. So I'm going to send this byte myself and then see if the machine does what I expect it to do, which often is the case. Sometimes you need a little bit extra, but that is mostly the process. And then from there, once you know those commands, maybe you can say, lock the plate down or move the plate to a specific location. And then what's that going to look like? And then you can it's kind of like a Sudoku puzzle where you sort of start with maybe the simple commands, and then once you have that filled in, you can recognize those commands in bigger captures and figure out what is the missing piece here, and sort of go from there.
That is so fun. I'm curious, when you talk about see what bytes come in, are we looking at zeros and ones, binary? What physically or visually are you looking at when you say bytes?
You could use the ones and zeros. I think mostly people like to look at hexadecimal characters, which is a little bit more concise notation. That is sort of the most basic level that people look at. Sometimes these bytes, they decode to actually text. But that is not always the case, but sometimes you can use one of these different standard encodings between bytes and text characters. For example, ASCII is one of the most famous ones, where, for example, the byte 32 is going to decode to a 2. And so sometimes you're able to decode your entire byte stream into just text, and then maybe you can recognize the numbers from there. At other times, the data is directly encoded. For example, an integer, which is a natural number, can be encoded into bytes more efficiently as well. In which case, more efficient typically means it's a little bit more complex on the other side.
So in one of our exchanges before recording today and talking, I was curious about and excited about the ability to use these large language models and essentially these kind of coding co-pilots as assistants to help with this reverse engineering process, or translation process or integration process, whatever the right word is. And you mentioned, I think one of the challenges specifically is the role of the tokenizer and how tokenizers are used and how they are can get in the way of the process that you just described. So could you maybe share more about what the current state and the potential state is of these coding co-pilots and helping these kinds of integration problems?
For sure.
Yeah.
So first of all, I do really love to use these tools. For GitHub Copilot is one of my favorites, and more recently OpenAI Codex. These tools, they're fantastic for writing code. For the process of reverse engineering specifically, I found them to be a little bit less useful because, like I just mentioned, there are these different byte streams that you sort of capture from the machine, and then you're trying to make sense of them. And for this, I found large language models, they're not so good at figuring out what is the pattern in these bytes. And one hypothesis for this is actually that it's because of the tokenizer. So maybe to just use an example that maybe people might be familiar with is you can ask large language models this question: how many R's are there in the word strawberry? And oftentimes it will tell you 2, even though that's the most, a 3-year-old can answer that there are 3 R's in strawberry. And the reason for this is that when computers they read these words, they don't go S-T-R-A-W. They sort of go maybe S-T-R-A-W in one unit of text, and maybe berry is another unit of text, or just however the tokenizer learned that is the most efficient way to represent data. So this is sort of getting into the technicalities where if you represent more characters using 1 byte or sort of 1 vector in the large language model, you can have text generated more efficiently. So for the companies, they love to use tokenizers as much as they can. But then since you're not looking at the individual characters, it's getting more difficult to actually understand in terms of the text that the user gives you, what specifically are the patterns in here. So you can imagine if you cannot count the words R and strawberry, how are you ever going to figure out in this byte capture, what is the pattern to these bytes? But maybe in the future, I think people are working on sort of more byte level encoders as the sort of compute resource grows. There's going to be more compute, so you can sort of use a little bit less efficient things. You can afford to do that. And so hopefully that's going to get better for reverse engineering and interpreting in that side. For now, I'm glad that I still have a job in looking at these bytes. But yeah, once you have figured out the pattern in these bytes, and for example, this byte that's number 17 or something corresponds to the open of a specific machine. Once you have this information in a text file, and I give it to chat, and then I also give this other backend in PyLabRobot to chat, it is able to pretty much write me a new backend. So it does save a lot of time sort of on the other side of interpreting the byte streams.